Hello, I'm Luis Serrano, and this video is about the binomial and Poisson distributions. So in this video, we're going to solve the following problem. Imagine that you have a store, and over the years, you look at how many people enter and realize that on average, 3 people enter the store every hour. And as far as you can tell, it's pretty homogeneous. Sometimes more people enter, sometimes less people, but there are no special rush hour or quiet hour specified during the day. It's kind of random. The question is, given this information, what is the probability that over the next hour, 5 people will enter the store? So in this case, the answer is 0.1008. But how did we calculate this number? This is what's called a Poisson distribution. But in order to learn this, first we need to look at a simple probability distribution, the binomial distribution. The binomial distribution is the following. My favorite way to look at distributions and a probability in general is with coins. So let's say that we flip a coin and the coin can land in heads or in tails. And now we're going to flip it many times, but let's say the coin is biased, so it doesn't land in heads or tails with the same probability. Instead, this coin lands in heads with a probability of 30% or 0.3 and in tails with a probability of 70% or 0.7. And now we're going to flip this coin 10 times and we're going to see what we get. So we'd imagine that it's more likely that the coin lands in heads 3 times, as the probability of landing in heads is 30%. So when we flip it, we can see that it landed in heads 4 times. So it's not exactly what we expected, but still close. So what we're going to do is we're going to run this experiment and calculate the average number of heads. So we can run this experiment many times, always recording the number of times we got heads and averaging that. Let's run it hundreds and hundreds or thousands of times. And what happens? Well, when we run it for a long time with lots and lots of tries, we can see that the number converges to 3 heads, which makes sense. This is the limit. So now what we get is this 3, which is 0.3 times 10, which is the probability of landing in heads times the number of throws in each run. And this is what happens in general. The probability that the coin lands in heads is P, and in each run we throw the coin n times, then the average is n times P. And this is what we call the expected number of heads. So now let's look at the probability of getting any number of heads if we throw the coin 10 times. Well, if we throw the coin 10 times, then 11 things can happen because the number of heads can be 0, 1, 2, all the way until 10. And for each one, we're going to calculate the probability. And I'm going to first give you the numbers and then show you how to find them. The numbers are these ones over here, and you can verify that they add to 1 because these are all the possible cases. Now, for each of the cases, we've highlighted one particular possibility, but think of all the ways a coin could land in each particular number of heads. For example, in the first case where it was 1 times heads, this can be in the first throw, or it can be in the second throw, or in the third one, or in any of the throws. Now also notice that the highest of these probabilities is for 3 heads. And that makes sense because the probability of landing in heads is 30%. So what I'm going to tell you next is how to calculate all these 11 numbers. But before calculating them, let's put them in a plot like this. Notice this time visually that the event with the highest probability is that the coin lands on heads 3 times out of 10. In this histogram, you can see that on the horizontal axis, you have 0 heads, 1 heads, 2 heads, all the way to 10 heads. And on the vertical axis, you have the probability. So this plot is precisely the binomial distribution. The parameters of this binomial distribution are the number of throws n, which this time is 10, and the probability that a coin lands in heads, which this time is 0.3. If we were to change the parameters of the distribution, the histogram will change. But it's always going to look like something like this with a bump in the middle. In fact, as n tends towards infinity, the binomial distribution tends to a normal or Gaussian distribution, something called the central limit theorem. But that will be a topic for another video. Okay, so as I promised, I'm going to show you how to calculate these probabilities. So here it goes. First, let's calculate the easiest one, which is when the coin lands in heads 0 times. That means each throw must land in tails. And the probability of the coin landing in tails is 0.7 for each of the throws. Since the throws are completely independent from each other, then we multiply this probability to obtain the total probability. So the answer is 0.7 to the power of 10, which is 0.02825. This is quite small, but that's the probability that all of them land in tails, so that we have 0 landing in heads. Now let's do one a little bit harder. What's the probability that only one of the throws lands in heads? Before answering that question, let's answer a simple one. What is the probability that the first throw lands in heads and all the other ones land in tails? Well, for the first one to land in heads, the probability is 0.3. And for the remaining 9 that land in tails, each one has a probability of 0.7. Therefore, the probability of all these events happening in that order, since they're independent again, is 0.3 to the 1, that's for the heads, times 0.7 to the power of 9 for the 9 tails, and that number is 0.012106. Now remember that this is not all. This is the probability that the first throw lands in heads. We're still missing the probability that any of the other throws is the one that lands in heads. So let's look at those. There are 10 ways in which one of the throws can land in heads and all the other ones in tails. And here they are. The throw that can land in heads can be the first one, the second one, etc., until the last one. And all of them have the same probability because all of them are 0.3 to the 1 for the heads times 0.7 to the 9 for the 9 tails. Now, since these events are disjoint, namely, no 2 of them can happen at the same time, the probabilities now get added, and there are 10 of them. So therefore, the probability that one coin lands in heads while all the other ones land in tails is exactly 10 times 0.3 to the 1 times 0.7 to the 9, which is 0.12106. And now let's do the same thing for 2 heads. So let's start by considering the probability that the first 2 throws land in heads and all the other ones land in tails. That probability, calculated in the same way as before, is going to be 0.3 squared times 0.7 to the 8. And that's for the 2 heads and the 8 tails. And so this number is 0.00519. Now the question is, in how many different ways can we have 2 heads amongst 10 throws? The number is 45. Why 45? Because 45 is the number of ways of picking 2 objects out of 10, also called 10 choose 2. All of these have the same probability as we saw before, so the probability of 2 heads, 8 tails is going to be 45 times 0.3 squared times 0.7 to the 8, which is 0.12106. As I mentioned before, this 45 is 10 choose 2, the number of ways to pick 2 objects from a set of 10, and those 2 objects are the 2 positions in which the coin lands in heads, and that also determines the 8 that land in tails. This number happens to be 10 times 9 divided by 2. Why? Well, because we have 10 possibilities for the first position of the H's, of the heads, and 9 for the second one, since one is taken already, and also we are counting them all in 2 different ways, because we're first counting the first coin and the second coin, but we're also counting it as the second coin and the first coin. So we're overcounting, and divided by 2 removes this overcounting. So let me elaborate a bit more on this way of choosing 2 elements out of 10. In the general case, let's say you have a set of n objects and you'd like to pick k of them. The number of ways of picking these k objects is given by the number n choose k, calculated as n factorial divided by k factorial times n minus k factorial. For any positive integer k, k factorial is the product of all the positive integers smaller than or equal to k, which is k times k minus 1 times k minus 2, etc., until 3 times 2 times 1. Actually, k factorial is the way of ordering k objects in a line. So for example, what is the number of ways of picking 3 coins out of a set of 10? Well, that's going to be 10 choose 3, which is 10 factorial divided by 3 10 factorial times 7 factorial. If you work out the ratios and cancel a bunch of repeated stuff, you're going to get 10 times 9 times 8 divided by 3 times 2 times 1, and that is 120. And in general, the probability of a coin landing k times in heads in n throws, where the probability of landing in heads once is the number p, is this number over here. N choose k times p to the k times 1 minus p to the n minus k. The first one is the number of ways to pick which k throws are going to be heads. The p to the k is the probability of those k throws that land in heads, since each one of them has probability p, and the 1 minus p to the n minus k is probability that the remaining n k throws land in tails, and the probability of one coin landing in tails is 1 minus p. And so this is a binomial distribution with two parameters, the number of throws, which is n, and the probability of heads, which is p. Now, if we calculate these numbers for, again, n equals 10 throws and p equals 0.3 probability of landing in heads and k from 0 to 10, we are going to get the following numbers. 10 choose 0 times 0.3 to the 0 times 0.7 to the 10 is the probability of 0 heads. 10 choose 1 times 0.3 to the 1 times 0.7 to the 9 is the probability of 1 heads, etc., etc., etc. And when we plug these numbers into a calculator, we get these numbers over here that I mentioned before. And when we put these numbers into a nice histogram, we get these for the probabilities. These are the numerical values. And so that is a binomial distribution. So next I want to do is show you a very, very special distribution called the Poisson distribution, which can be seen as a limit of binomial distributions in a very interesting way. So the Poisson distribution answers the following type of question that I mentioned before. Imagine that you have a store and throughout the years, you see people entering and leaving, and you take an average and notice that on average, in particular hour, 3 people enter the store. And now the question is the following. Given this information, what is the probability that over the next hour, 5 people will enter the store? So the number are the following. It's e to the negative 3 times 3 to the 5 over 5 factorial, which is 0.1008, etc. E over here may look familiar. It's the Euler number, 2.7182, etc. And it's one of the most important numbers in mathematics and statistics and physics and many, many, many fields. I would say it's up there with pi. But the great thing is that this formula is universal. The 3 and the 5 are arbitrary. If you counted and said that 8 people arrive every hour, and what's the probability that 2 people enter the store over their next hour, that's e to the minus 8 times 8 squared over 2 factorial, which is 0.01073, etc. And in general, if the average number of people that enter per hour is lambda, and you want to find out the probability that k people enter the store in the next hour, then that number is e to the negative lambda times lambda to the k over k factorial. That is precisely the Poisson distribution. Now the question is, how do we calculate this number? The expression was complicated, but actually follows from the binomial distribution using a limit. Let me show you how. So in order to solve this problem, we're going to start with a simpler one. Imagine that in our store, we don't really want that many people at the same time. Maybe there's a pandemic, and we can only have one person at a time. So we open 10 intervals of 6 minutes each, and only one person can come at each interval, and they must leave when the interval finishes. Now in this simplified problem, we keep track of visitors and find out that on average, 3 people are visiting the store per hour. Does this problem sound familiar? Well, it's very similar to the one of the coins, because take a look at all the other intervals. Nobody arrived at any of those 7 intervals. That's the same as tossing a coin 10 times and the coin landing in heads 3 times, corresponding to each of the times a person entered the store, and in tails 7 times, corresponding to each of the times a person did not enter the store. So we know that probability. That's the same as the probability of getting heads 3 times. And that's the binomial distribution where p of heads is 0.3 and p of tails equals 0.7. So in this particular problem with the intervals, the number of people arriving in the store is modeled by the binomial distribution. So, for example, what's the probability that 5 people enter the store in the next hour? Well, that's the same probability that we toss a coin 10 times and that the coin lands in heads 5 times, corresponding to the times that people arrived, and in tails another 5 times, corresponding to the intervals where nobody arrived. And so the probability that 5 people arrive over the next hour is the same probability that if we throw this coin 10 times, the coin lands in heads 5 times, and that's 10 choose 5 times 0.3 to the 5 times 0.7 to the 5. Where again, this 10 choose 5, the number of ways to pick the intervals in which 5 people arrived. This 0.3 to the 5 is the probability that people arrived at those intervals, and the 0.7 to the 5 is the probability that nobody arrived at the other intervals. Now, something very important here is that this 0.3 is 3 over 10, and this 0.7 is 7 over 10. So now what we're going to do is we're going to change this 10 to different numbers, 20 and 60 and anything we want, and these probabilities are going to change. So let's say that we realize that 10 intervals is too little. So we decide to divide the hour into more intervals, say 20 intervals, each of 3 minutes. And what happens now? Now we want the probability that 5 people will enter the store over the next hour. Well, just like before, except that now we throw the coin 20 times, it lands on heads 5 times, and on tails 15 times for all the times that nobody entered the store. But now, what's the probability that the coin lands in heads or tails? Well, recall that on average, we still have that 3 people enter the store at every hour. This still happens, and so therefore, this is a binomial distribution where the probability of heads is now 3 over 20, and the probability of tails is 17 over 20, because on average, 3 people enter the store. That means that on average, the coin lands in heads 3 times out of 20, and that means that the probability of heads is 3 over 20, and the probability of tails is 1 minus that, so it's 17 over 20. And on this binomial distribution, the probability that 5 people arrive over the next hour is the same as the probability that 5 coins landing in heads, which again is 20 choose 5 for the positions, times 3 over 20 for the probability that people arrived, and times 17 over 20 for the probability that people did not arrive. And we can continue doing this. We can subdivide the hour, let's say now, into 60 intervals of 1 minute each. And so now we have this binomial distribution with probability 3 over 60 of landing heads and 57 over 60 of landing tails. And we want the probability that we tossed this coin 60 times and it landed on heads 5 times. So that's going to be 60 choose 5 times 3 over 60 to the 5 times 57 over 60 to the 60 minus 5. And we can continue doing this in even smaller and smaller and smaller intervals. So let's say there's n of them, and we want to see the probability that 5 people arrived, and the binomial distribution is the one where p of heads, or p of person arriving, is 3 over n in an interval, and p of tails, which is no person arriving at that interval, is n minus 3 over n. And so the probability that 5 people arrive in this binomial distribution is n choose 5 times 3 over n to the 5 times n minus 3 over n to the n minus 5. And so now basically we're going to let n go into infinity, because if you imagine, if n is infinity, then that's the original problem, because people can arrive pretty much at any second of the hour or at any instant. And so what we need to do is let n go to infinity and see where this formula goes. So first, let's look at some numbers. And these numbers are the probabilities we obtain when we split the hour into different numbers of intervals. So when we split the hour into 10 intervals of 6 minutes, the probability of 5 people arrive is 10 choose 5 times 3 over 10 to the 5 times 7 over 10 to the 5, which is 0.1029. If we divide into 20 intervals of 3 minutes, then this is the formula, which is 0.1028. If you divide into 60 intervals of 1 minute, then it's this number, which is 0.1016. If you divide into 3,600 intervals of 1 second, then this is the number, and it's 0.1008. So these numbers are sort of converging somewhere. Let's say we divide it into 3,600,000 intervals of 1 millisecond. This is the probability now, and that's 0.1008, etc., etc. And the idea is to see the limit of this, or where do these numbers converge. So at the end of the universe, at the end of doing this process infinitely, we're going to have an interval of 1 hour splits into lots and lots of tiny intervals of a tiny amount. In principle, we have infinitely many intervals of length 0. Now, plugging in infinity here is difficult. We're not going to get a number, but what we can do is use calculus. We can call it the limit as n goes to infinity of n choose 5 times 3 over n to the 5 times n minus 3 over n to the n minus 5. That is the probability that 5 people enter the store if we subdivide it into infinitely many intervals of 1 instant length. And that's the probability we were looking for at the beginning. This number is 0.1008. And how do we calculate this number? Well, let me show you soon. But first, let's plot these numbers. And notice that the probability of 5 people entering the store in the next hour is somewhere at the limit at the very, very right. In this plot, on the horizontal axis, we have the number of intervals. On the vertical axis, we have the probability. And as you can see, the horizontal axis is logarithmic. And so the limit is some number over here. where this number is where this sort of blue line converges in infinity, and the value is 0.1008, and that is precisely the probability of 5 people entering the store in the next hour. But now I still haven't told you how to calculate this 0.1008. So let me show you how using algebra. So the way we're going to do it is the following. The probability that 5 people enter the store is n choose 5 times 3 over n to the 5 times 1 minus 3 over n to the n minus 5. And what I want to show you is that as n goes to infinity, this actually converges to the expression 3 to the 5 over 5 factorial times e to the negative 3, which is this number we saw before. Recall that e is the Euler number, 2.71828182, etc. Which, if you want to know more about it, check out this video that I have over here in my channel, where different expressions of e are explained, in particular one that we're going to need pretty soon. So let's get back to the math. The red part, n choose 5, can be expressed as n times n minus 1 times n minus 2 times n minus 3 times n minus 4 divided by 5 factorial. The blue part is 3 over n to the 5, which is 3 to the 5 over n to the 5. And the green part is 1 minus 3 over n to the n minus 5. I'm going to take that n minus 5 and split it into n and minus 5. So we get 1 minus 3 over n to the n times 1 minus 3 over n to the minus 5. Now let's break it down even more. Look at that 1 minus 3 over n to the minus 5. That 1 minus 3 over n can be expressed as n minus 3 over n. And now let's get rid of that pesky minus 5 exponent, because that's the same as n over n minus 3 to the 5. Now, we have an n to the 5 on the bottom and an n to the 5 on the top, so they get cancelled. And now, let's look again at the red number. These are n times n minus 1, n minus 2, n minus 3, n minus 4. We're going to divide them by these 5 n minus 3's we have over here. Now, the blue 3 to the 5 stays the same, the red 5 factorial stays the same, and now what remains here is this 1 minus 3 over n to the n. We're going to deal with that in 1 minute. Now, as n goes to infinity, take a look at any of these numbers. Any of these ratios tend to 1, because n over n minus 3 and n minus 3 get more similar and more similar as they go to infinity in terms of ratio. So all these ratios go to 1 when n is humongous. Think about the number 10 million. 10 million over 10 million minus 3 is very, very, very close to 1. And as n goes to infinity, these are all converging to 1. The 3 to the 5 over 5 factorial stays the same. And now here's the interesting thing. 1 minus 3 over n to the n converges to e to the minus 3, the Euler number. And again, if you want to see this, check out this video. In there, I explain why the limit of 1 plus x to the n is equal to e to the x. That's one of the main properties of the Euler number. As a matter of fact, it can be one of the defining properties of the Euler number. So that means that this entire product converges to 3 to the 5 over 5 factorial times e to the negative 3. And that number is precisely the number of the probability that 5 people enter the store in the next hour. So let's recap. You have a store where on average 3 people enter per hour. And what's the probability that 5 people enter the next store in the next hour? Well, it's 3 to the 5 over 5 factorial times e to the minus 3. And we got that using a limit over smaller and smaller and smaller intervals. Now, what happens if some number, lambda, people enter per hour, where lambda doesn't have to be an integer because it's an average. It can be 7.314 or whatever. What is the probability then that for some integer k, this time k is an integer, that k people enter the store in the next hour? Well, this probability is lambda to the k over k factorial times e to the negative lambda. And all you have to do is the same exact procedure, except change the 3 to a lambda and the 5 to a k. And that, my friends, is the Poisson distribution. Here is a histogram of it, where in the vertical axis you have probability, and in the horizontal axis you have the number of people entering the store in the next hour. So here's the probability that 0 people enter the store, probability that 1 person enters the store, 2 people enter the store, 3, 4, 5, 6, etc., all the way to infinity. Notice one thing. Notice that the highest probability is at 3, because if 3 people enter the store in an hour, then most likely 3 people will enter the store over the next hour. Here 2 and 3 are actually the same, but that's an anomaly. Normally it's the same, is the number of people entering the store, the highest probability. Also notice that all these numbers are actually bigger than 0. So for any n, there's a non-zero probability that n people enter the store. Now, for example, the probability that 500 people enter the store of the next hour is very, very, very tiny, given that only 3 enter on average, but it's still possible, and the probability is just a very, very small number that is bigger than 0. Now, notice that all these blue bars add to 1, because over the next hour, some number of people are gonna enter, so the sum of these probabilities is actually 1. And so that's it. That is the Poisson distribution. So that's all, folks. I hope you enjoyed this video. I'd like to remind you that I have a book called Grokking Machine Learning that I invite you to take a look at. Here's the link also in the comments, and there's a discount code for a 40% discount, Serrano YT, for the users of this channel. It's a book where I explained a bunch of the supervised learning algorithms in detail, also with like fun examples and also with code. So thank you very much. If you enjoyed this video, please subscribe for more content. Please hit like or share among your friends, and also throw in a comment. I really enjoy reading your comments. In particular, if you have other videos you'd like to see, feel free to comment there on the topics. You can also find me in Twitter at LuisLikesMath, and if you'd like to see all this information put together, check out this webpage, serrano.academy. There I have blog posts, videos, anything I write goes there. So thank you very much, and see you in the next video.